NMR spectrum, similar to IR. This is not teaching IR and NMR. It's just kind of introduction and the application of IR and NMR in the lab. NMR scale for NMR is 0 to 10, and 0 to 10 without a scale from 10 to 12. If the compound contains, this is basically proton NMR that we are talking about. For proton NMR, hydrogens would show signal in the NMR spectrum. If the hydrogen is coming from carboxylic acid, would show a signal out of scale between 10 and 12. So very easy to identify your compound is carboxylic acid or is not carboxylic acid. If the hydrogen is coming from aldehyde, if it comes from aldehyde, this hydrogen would show a peak at 9. So we see 9 for the aldehyde. So if you have a peak here, definitely we know that we have COH or CHO. Basically, we have aldehyde. This one is going to be carboxylic acid. If we have a peak anywhere between like a short and broad peak, anywhere between 2 and 5, that would be NH. NH and OH, they don't have like very specific location, but for both of them, it's going to show like a short peak and a short and broad peak due to the hydrogen bonding. For NH is going to be between 2 and 5, and for OH is going to be between 2 and 7 or 1 and 6. So if you see a short peak, that's either NH or OH, and you have to have other evidences like a mass spectrum, or you have to have IR to see if it has a spike. For NH, then it's coming from NH. No spike means that is OH. The CH3, this is the terminal carbon in alkane or alkyl group, would have a signal around 0.9. It's showing the range because of the electron withdrawing group and all that, but is 0.9, I would say. If it's a CH2, that means a secondary carbon or secondary hydrogen, it shows a signal at 1.2. If it's a tertiary hydrogen attached to tertiary carbon, 1.4, and the range would be 1.4 to 1.7. If the hydrogen is attached to carbon that directly attached to oxygen, so you have like a ether, so you have a CH2 here, okay? This hydrogen would show a peak between 3.5 to 4. Okay? Same thing here. This is very similar. Is the hydrogen that is attached to carbon directly to hydrogen. This could be alcohol, but what is concerning us is this. Carbon is directly attached to the hydrogen. If it's alcohol, you would see this hydrogen between 3 and 4. Or if it's coming from ether, it is not showing the oxygen, it's showing the hydrogen and the carbon adjacent or attached to oxygen. Electron withdrawing group would increase this value. So if we have a CH3 at 0.9, if there is a Br on the same carbon, it's going to increase that to like 3.5. And that's for bromine. For chlorine, because it has slightly higher electronegativity, 3.6 to 3.8. Then we have this one for, this is for the aldehyde, is going to be, this one is going to be around 9. But if you have a CH2 or CH3 next to the aldehyde, that is going to show a signal around like 2.5 or 2.1. Hydrogens are, it's adjacent to CC double bond, is not on the CC double bond, but is adjacent to CC double bond. A pi system acts as electron withdrawing group, and it's going to increase that number, and it's going to go to increase to like 1.9. If it's aromatic, that's again a pi system, a stronger pi system. It's going to be around 2.3, so between 2.2 and 2.5. If a nitrile group is attached to it, it would go to between 2 and 2.5. If it's a carbonyl group attached to it, so you see the pattern, these are all electron withdrawing groups. It could be a pi system, or it could be electronegative element attached to it. That is going to increase the frequency or the number that on the ppm number that the signal appears for any of these hydrogens if it's attached to electron withdrawing group. So this counts like electron withdrawing group for positive and negative, partial negative that we have here. This carbon is positively charged and it pulls electron from the carbon. So the hydrogen on this carbon is going to be de-shielded more. So electron withdrawing group would de-shield the hydrogens from electrons. So when it's de-shielded, that number is going to be downfilled or further away from TMS. TMS, the signal that appears at 0. This is a tetramethyl cellulose is going to show a peak at 0. That's for highly shielded hydrogen. So when you have this compound, electronegativity of Si is lower than carbon. So it doesn't pull any electron from hydrogens. So this is like highly shielded. So it would show at 0. When it comes to COOH, which shows a peak between 10 and 12, highly de-shielded, so highly electronegative elements, or this molecule, this group is pulling electrons strongly from hydrogen, and compared to the TMS is going to be at the extreme high number between 10 and 12. For aldehyde, is going to be between 9 and 10. So electron withdrawing group is going to increase that number compared to the TMS. So when we said CH3 appears at 0.9 for CH3, and then for CH2, 1.2, for CH is going to be 1.4. Those are like engaging of the electrons, or pull electrons is removed from the hydrogen and being de-shielded. And then these numbers are relative numbers to this internal standard of TMS. Pi system is electron withdrawing group. Electron withdrawing, high electronegativity is electron withdrawing group. A positive charge on a carbon, anywhere you see that if the carbon is attached to oxygen, or if it's attached to like chlorine, this carbon has a positive charge, so it's electron withdrawing group. So if this is attached to another carbon carrying a hydrogen, another carbon carrying a hydrogen, this hydrogen is going to be affected and is going to be de-shielded. And if it's de-shielded, would be further away from TMS. Basically, it appears at higher number. So that is basically the concept. And that's what I, usually in lecture, that's what I start with, the basic, how the machine is designed and what are the basic for it. But in the lab, we are looking for these numbers. The numbers are more important for us. Where the signal is located, location of the signal has to do with the type of hydrogen, shielded or de-shielded hydrogen. So for this CH2 here, the pi system is on the same carbon, so it's going to deshield this hydrogen a lot more than this system here. So because there's a distance, but this carbon is directly attached to the pi system, so it's losing electrons to the pi system, and the hydrogen is going to appear between 5 and 6. Aromatic hydrogens, this is very significant for any identification. The first thing you want to look at the signals between 7 and 8. If there is no signal, your compound is not aromatic. But if there is a signal between 7 and 8, your compound is going to be aromatic. Now, electron withdrawing group is going to increase that number. Conjugation would lower that number. That's why we have broader range here. But 7 and 8 is a safe place to look for. If there is a signal here, your compound is aromatic. If there is a signal between 5 and 6, your compound is alkene. For alkyne, this terminal alkyne would show a peak between 2 at 2.5. sp, again, a highly electron withdrawing group that is attached here. For esters, we don't see a signal for oxygen or oxygen here, but we do see a signal for this hydrogen that is attached to ester at like a 2.5 to 3. For CH2 that is attached to nitrogen, nitrogen is directly to the nitrogen, that's electron withdrawing group. So just like chlorine or just like oxygen, this also is going to show higher number. For oxygen, it was 3.5 to 4. For nitrogen attached to this carbon is between 3 and 3.5. Electron withdrawing group on the same carbon, if it's halogen or if it's oxygen, is going to increase that number, 3 to 3.5. So if you know these numbers, then you can identify your unknown. If, for example, you were trying to make aldehyde, did the aldehyde form, the aldehyde functional group formed or not? If you were trying to make alcohol, right, by reduction of the aldehyde, a peak between 1 and 6, a broad and short peak between 1 and 6, that's the indication that alcohol has formed. Just looking at this as an example and comparing to the table we had NMR spectroscopy said for this compound is aromatic, and there is a methyl group attached to the aromatic. These hydrogens are going to be deshielded by this pi system, and this is going to, the signal for the hydrogen, which is benzylic hydrogen, would show around 2.5, and that's what we have between 2 and 2.5. We have a signal that is showing for that CH3. And the signal between 7 and 8, it shows the aromatic hydrogen. So these are A hydrogen, and this one is a B hydrogens that we have here. So what would be the difference between this CH3 on the right, I'm going to label A, and a CH3 for B? CH3A is attached to another carbon, but CH3B is attached to oxygen. So this is going to appear, this one is going to appear between 3 and 4, but this one is going to appear between like 1 and 2, because this oxygen is in the molecule. If we didn't have the oxygen, this would be at 0.9, but since we have oxygen on the neighboring, it's going to deshield this slightly, but it's not a direct effect. So it's going to appear between 1 and 2. The other information that we can use from NMR is the splitting pattern. When it comes to the splitting pattern, the rule of n+1 is going to apply. So this hydrogens is going to appear between, the signal would be between 1 and 2, but it's going to be a triplet because two hydrogens are adjacent to it. So we see a peak that it's like this triplet. The hydrogens from CH2, on this side, there is no hydrogen, but on the right side, we have three hydrogens. So for this, we will get a quartet. And for this one, there is no hydrogen, there is no carbon adjacent to it. So is an N+1, where N is the number of hydrogen on adjacent carbon. Adjacent, there is no carbon. So N is 0 plus 1. So we are going to get a singlet. So this would be singlet, a quartet, and a triplet. If you have, these are some of the examples that it helps you with like a shortcut. When you have isopropyl group, this hydrogen from isopropyl is going to show a splitting pattern of septet, because you have 6 hydrogen on adjacent carbons plus 1, so it's showing septet. And the hydrogens in the here, this is going to show doublet, because you have only 1 hydrogen on the adjacent carbon. Have another IR NMR example. So you would check that for the, if you have a peak over 3000, that means alkene is present. If you have a peak around 1600 and 1500, then that means you have aromatic compound. You have a peak between 7 and 8, then that is aromatic compound. So we know that we have aromatic compound. For alkyne, we have a peak at 2200, and for CH is going to be at 3300. Okay. So there's some helping an interpretation of the IR and the NMR. When what is not present is not the solution. You have the solution, so you just please check the structure formula for the compound and decide which peak corresponds to which functional group from the or bond from that compound. Okay, that's basically it. I'm not trying to teach the IR and NMR here. I'm just trying to see some of the application for the lab purposes, and please read the rest of the explanation in the lab manual and try to interpret the examples. Thank you.